recording device.
Yeah. Wait, it's okay. We're okay.
Okay. So if I had a methyl group, an ethyl group, a hydrogen, and a bromine, this carbon is bonded to 4 different groups. Again, it doesn't matter that these are both carbons in this story, it's about the whole thing. If you draw a mirror next to it, we're now going to reflect through that mirror. So things that are close to the mirror will stay close to the mirror. Things that are coming out into the room will stay coming out into the room. So this should be the methyl, and this should be the ethyl. The bromine, which is in the plane of the board, should still be in the plane of the board. And the hydrogen that's in the plane of the board should still be in the plane of the board and farthest from the mirror. Do you agree that this is a mirror image if this is the mirror? I'm going to try to superimpose these 2 molecules, everybody. That is, I'm going to try to see if they are the same molecule. So what I'm going to do is I'm going to take this hydrogen and I'm going to swing it around to the left side. Or, said differently, I'm going to rotate around that bond 180 degrees. So here we are rotating. The bromine is going to stay in the same place because that's the axis of my rotation. And if I take this hydrogen that's over here and rotate it 180 degrees, it is going to be over there, pointing at the eye wash. So again, I chose this so it would match. But this methyl group that is currently pointed, you know, where Luke might sit should he ever come back to class, if we rotate it 180 degrees, it's going to be pointing to the bathroom. It's going to be behind the plane of the board. And that ethyl that's currently at the stairs, if we rotate it 180 degrees, it's going to be pointing directly at me. Are these 2 molecules the same? They are not the same. The ethyl and the methyl are flipped. These 2 molecules are not superimposable. You identify this by having a carbon that is bonded to 4 different things. Everybody likes it when I talk biology. Every time you draw this, what do you have? Have an amino acid, but you have a carbon that's bonded to 4 different things in 19 out of 20 cases. If you have the amino acid glycine, 2 of these things are the same. It is not chiral, but every other amino acid is chiral, and every single amino acid in your body has the same handedness. Is that not crazy to you? All things that are chiral are not superimposable with their mirror image. Every amino acid in your body is chiral, save glycine. But what's strange to me is that they all have the same handedness. So we're saying this molecule exists like a right and left hand. But what's weird is in you, a living organism, and all of the other living organisms, all of the hands that make up your proteins are one of them. Same handedness.
I don't understand same-handedness.
So is it like, okay, I could have an amino acid in my body that's on the right hand, and someone else?
Everyone's going to say, all of us, every living
Everyone
organism,
has the right hand.
everyone has the right hand one.
So then, what is the left hand?
It is not effective in building protein. Just like if you think about glucose, can you imagine your alpha glucose?
Sure.
Can you imagine your beta glucose?
Sure.
Like I'm just taking one OHH and flopping it over. Much like here, all I did was change a methyl and an ethyl around 1 carbon bond. One of those makes delicious starch, something my body can process as food. The other one makes boring fiber. I can't use that as food at all. The only difference between those 2 things is the orientation around a singular chiral carbon. So chirality matters a great deal in both organic and biological chemistry. For those of you who like stories from the past, thalidomide was used as a morning sickness drug in Europe in the 70s. sick when they're pregnant, right? The new chemical company decided to make thalidomide, and instead of making just the right hand, which was a great morning sickness drug, they made both hands. And the left hand was a strong mutagen. It made the babies not grow limbs.
Oh.
So this is super important in drug design. We call it asymmetric synthesis to only make the chiral compound you want. And next class, we're going to talk about how this relates to SN1 and SN2. So any of you who feel like you haven't mastered SN1 and SN2, we're going to go back through those mechanisms, but we're going to think about them through the lens of, ooh, is that molecule chiral?